Hello, Tensor friends. We're in the third the video of this set we're doing on Gaussian curvature. So in video number one, we looked at the Gaussian curvature in a flat manifold, and we derived this equation. And we said that the Gaussian curvature K is equal to the magnitude of this vector. Okay. Then in video number two, we stepped up our game to do the Gaussian curvature of a curved manifold. And we said the Gaussian curvature was equal to the determinant of the second fundamental form divided by the determinant of the first fundamental form, which is the metric tensor. Now in this case, we're going to look at Gaussian curvature using the Gaussian curvature tensor. This guy's got a lot of stuff named after him. Okay, here is the format of the tensor I'm going to use, and we'll talk about what all this is in a minute. I did an entire playlist on this, and I'll leave a video link in the description. It's long, it's tedious, I admit it's somewhat boring. Actually, it's very boring. But there's a lot of really good tensor calculus in there. And so if you really want to know where this comes from, I'll leave that link and you can at your leisure. Okay? Now, let's do a little background here. We have a surface, a manifold, with the surface. We're only interested in the surface of this manifold, and it is embedded in a larger space called the ambient. Okay, so anything related to the surface, you use the Greek indices. Anything related to the ambient, you use Latin indices. So if we have a position vector on our manifold, it is a function of the surface coordinates. But these surface coordinates are embedded in an ambient space. Okay, so they are also a function of the ambient coordinates. So we have a compound argument here. I hope I explained it right. So if we take the derivative of this position vector with respect to a surface, the coordinate, we can use the chain rule such that the change in this position vector with respect to the ambient coordinates times the change in the ambient coordinates with respect to the surface, the coordinates. Okay, so what is the derivative of a position vector with respect to coordinate? Well, it's a basis vector. So this is the S alpha basis of the vector. And here's another one. This is the one we're used to, which is EI. Okay, so now we have an equation that relates the surface basis vectors to the ambient basis vectors via whatever this is. The change in the ambient coordinates with respect to the surface coordinates. Well, this thing has a special name. It's called the shift tensor, ZI alpha. So it has mixed indices, and it has an ambient index and a surface index, which matches these two, right? Okay, so how do we find that thing? Well, we have two surface coordinates, u and v. So alpha can be 1 or 2, but I is the ambient space, so it could be 1, 2, or 3, right? So here's our generalized equation. Now there's only one free index in this equation, alpha. Do you see it? This is a summation index. So if we say S1, which is u, so here's our free index, 1, there it goes, 1, 1, 1. The summation index, 1 in the first case, 2 in the second case, 3 in the third case. Exact same thing for S2. Okay, so now we've got to find these components of the shift tensor, and by definition they are this. So as an example, the derivative of this is just x with respect to u. This is x with respect to v. This is y with respect to u. This is y with respect to v, etc. So all we got to do is take those derivatives using the parameterization that we used for the hyperbolic paraboloid. Remember? In the last video? So we get this matrix. 1, 0, 0, 1, 2, minus 2. So our surface basis vectors are actually just the components of this matrix. So SU is just 1, 0, 2U, right? So there's 1 EX, 0 EY, 2U EZ. SV is 0 EX, 1 EY, minus 2 EV. EZ. Okay, so here's our surface coordinates, which in this case are exactly the same thing as EU and EV we would normally do. I don't know if that's true in all cases. It's true in this case. Okay, now here's that equation. I'm just going to present it. If you're interested, please watch the playlist. And what this is saying is that the Gaussian curvature tensor is equal to the negative of the shift tensor multiplied by a change in the normal coordinates, the normal components with respect to the surface coordinates. Now, so this is the components of the normal. The normal is in the ambient space because it sticks out of the manifold, right? It's up into the 3D, so it's not on the surface anymore. It's in the ambient space. All right, so we have to find our normal first, and we did that in the last video by taking the product of in the last video it's called RU and RV, but this is exactly the same thing. All right, so we got in the last video we got this normal. Now we need to just take the derivatives of these components, not the vector, the components, with respect to the surface, the coordinates. So the first surface coordinate is u, so the derivative of this is, with respect to u, is -2. This is 0, this is 0. With respect to v, this is 0, this is 2, and this is 0. Okay? Now we got enough to find our Gaussian curvature, the tensor. So we multiplied these two matrices together. So this one times this one, and we get this 2, 0, 0, -2. Now, from the video where we were looking at the second fundamental of the form, it looked like this: 2, 0, 0, -2. Isn't that cool? It's exactly the same thing. I thought that was interesting. Excuse me. Okay, so we have B alpha beta, but we want this. A fully contracted tensor is going to give us the invariant that we want. Okay, so how do we raise an index? Well, we use the metric tensor. In this case, it's the inverse metric tensor, or the contravariant metric tensor, however you want to say it. So the components of this times the components of that will raise this index and give us this fully contracted tensor. Okay, so in the last video, once again, we found the tensor, and in this video, it's the tensor. Okay, and here it is, but I need its inverse. And at first, I just said, oh, I'll just take its inverse and go on with it. Well, it's just an algebra nightmare. So you know what I did? I went to an online calculator and I said, diagonalize this rascal, and it did it. And here's it diagonalized. And you're saying, why did you want to do that? Because this is why. The inverse metric tensor is now this easy. Just put these two things under one, because these off diagonals are zeros. So I don't have to do anything hard. This made it so much easier because the algebra was just killing me. Okay, so here's our generalized equation. So B11 would just be B11, which was, what's B11? Okay, here it is, 2, 0, 0, -2. So it's 2, and G11 inverse is 1. And both of these are 0, both of these are 0. And B22 was -2, and G22 was this. Okay? So now we got our matrix. 2, 0, 0, and this. Now, the Gaussian curvature is given as the determinant of this fully contracted tensor. So it is just this times this minus that times that. So you get -4 over this, which is exactly the same thing we got when we did it the old-fashioned way. So the new way and the old way agree 100%. Okay? So that's that, and the next time I'm hoping to do this with Riemannian geometry. All right, see you later.